Quest seminar with Tom Mitchell as our guest. I'm so happy to have Tom here. I've known Tom for a long time, and I just discovered I went to read about his background just a little bit, just to get, and I didn't realize he had actually done an undergraduate degree here at MIT in electrical engineering, so we have that. And then he showed up at Stanford in 1979 You finished in 1979. That's right. Okay, good. That was the year I showed up, actually, at Stanford as an undergraduate. So we possibly passed in the hallway. But so Tom has been working on machine learning since way before it was cool. One of really the first people inside computer science to think about how it is that we get data and form hypotheses. And I was just telling him that one of the foundational ideas, I think, from his thesis was this idea of version spaces, how you can think algebraically about the whole set of hypotheses that's consistent with the data that you have. And I actually have a student who's just finishing his thesis right now who's using that idea. So there's still kind of really deep and fundamental things to be gained from Tom's work. He was, I think, the first department head in the machine learning department at CMU, was really foundational in setting that up. The first machine learning textbook, and I guess NEL was a thing that he has been working on, maybe not super recently, but up to maybe 5 years ago or so. The idea of a system that could scrape the web and find information and be never-ending learning agent that would discover things and use the things that it discovered to help to discover new things. And I kind of feel like what we're seeing now in the large language models is a very NEL-like thing. So I don't know, Tom has been a great progenitor of machine learning in the field, and he's going to tell us about the history starting a lot longer ago than that. So welcome, Tom.
Thanks, Leslie. Thanks, everybody, for being here. Let's see. People ask me, and I bet they ask you, if you're an AI person, how did we get to this amazing place where we have these fantastic AI systems? And my answer to that is we worked for 50 years trying to build intelligent systems by hand. And then about a decade or so ago, we realized it's a lot easier instead to program them to learn and then just have them learn to be intelligent. And that's actually what got us to today's LLMs and ChatGPT and these amazing systems. So the real question is, how did machine learning get here? And that's what this talk is about. This is not a typical, here's my research talk. This is a talk that actually grew out of my friends at Carnegie Mellon saying, Tom, can you give a guest lecture in the intro machine learning course about the history? And then I started talking to other people, and it led to this. Okay, so we're going to talk about the history of machine learning. And if we're going to do that, we should start with the first people we know of who looked at learning and how it's even possible in humans. That would be Aristotle, who was interested actually in the question of how people could look at concrete instances of things, think a tree, for example, and learn the general essence of the concept. That was Aristotle. About 100 years after that, there was a school of Greek philosophers called the Pyrrhonists, and they really focused specifically on the question of induction. That is, how can you look at specific examples and learn something general from it? And they were interested in, can this really be justified? So imagine if during your lifetime, all of the swans that you've seen are white. Should you conclude that all swans are white? What's the justification for going beyond what you've actually seen? So this discussion goes on for a while. In the 1300s, William of Ockham came up with what we call Occam's razor, which is you should prefer the simplest hypothesis that fits the data. So by his razor, if all of the swans you've seen are white, you should conclude simplest hypothesis, all swans are white. In the 1600s, Francis Bacon I think, added a lot by pointing out the importance of collecting targeted data to test your hypotheses. And in the 1700s, the philosopher David Hume really kind of nailed the problem of induction. He argued very persuasively that really it's not possible to generalize beyond the data you see unless you're willing to make some assumptions. And he pointed out even the assumption that the future is going to be like the past is an assumption, and we don't have a proof of that. So his point was that induction is maybe a helpful habit that people follow, but it's not really something that we can justify as in proving that it's a legitimate thing to do. So this discussion has gone on for a long time. When computers came out in the 1940s, Alan Turing noticed and pointed out that maybe computers could learn. He said, instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. So he had the idea that computers could, maybe should learn, but he did not have an algorithm for how. That waited until the 1950s, and there were two important events in the 50s. One was due to Art Samuel, who was an IBM researcher. He developed a computer program that learned to play checkers very well. And I'll just read a couple of sentences here from his paper, abstract. 2 machine learning procedures have been investigated in some detail using the game of checkers. Enough work has been done to verify the fact that a computer can be programmed so that it will learn to play a better game of checkers than can be played by the person who wrote the program. So he really had, to my knowledge, the first computer program that exhibited the ability to learn something interesting and, in fact, to outperform the person who wrote the program. Now, this was very important work and actually seminal in the field. If you ask, what did his program learn? It learned an evaluation function that you give it an arbitrary checkers board position, and it assigns it a numerical score. The higher, the better the board position is from your point of view. How did he learn that? He learned it by having the program play checkers games against itself. And those two ideas actually persisted through the decades and were used by the programs that eventually beat the world champion backgammon player, the world champion chess player, and the world champion Go player. So he really had an idea that stood the test of time. The second thing that was important in the 1950s was the invention of the world's simplest neural network called the perceptron by Frank Rosenblatt, a Cornell researcher. And he was actually a neuroscientist interested in how is it that the brain could use these neurons to absorb information and then use that information later. And he built a computational model in which the perceptron would have an input set of activations provided by a sensory organ like a retina. And the output would be another set of activations generated by neurons that would produce outputs depending on these inputs and depending on numerical weights associated with the edges. And what got learned here were those numerical weights. So this was important because it actually catalyzed a great deal of work over the next decade, where people then adopted the idea of perceptron-type learning and explored alternative algorithms for learning the best weights and from what kind of data and so forth. So during the 1960s, the theme of work in this field was mostly around perceptrons. And in 1969, two MIT scientists, Marvin Minsky and Seymour Papert, wrote a book called Perceptrons that kind of summarized work up to that point. But the book also, sadly, to some people, proved that there were a lot of things perceptrons would never be able to learn because they couldn't even represent any nonlinear function. They could only represent linear functions. So for example, if you have two inputs and you want the output, and the inputs could be 1 or 0, and you want the output to be 1 if either one of those inputs is a 1 and the other is a 0, but you want it to be 0 if they're both a 1, even that simple exclusive OR function cannot be represented by a perceptron. Actually, John McCarthy famously stated around that time or a little later, a program will never be able to learn what it can't at least represent. And that was really the summary of this point. So this book actually kind of killed off research in perceptrons because people then realized it seemed like a dead end. Okay, so now if we're not going to work on perceptrons, what are we going to work on? And it turns out Minsky had a Ph.D. student named Patrick Winston here at MIT. And Patrick, his thesis came out in 1970, and he had a different idea. Instead of learning perceptrons, what if we learn what we'll call symbolic descriptions of these concepts? So for example, in his thesis, he would train a system with positive and negative examples of line drawings of structures like an arch. And his program would learn a symbolic representation like this that would say, for example, this one says, an arch could be two rectangular things that do not touch, but which both support something else, which can be any shape. And his program learned this kind of symbolic hypothesis by incrementally updating it each time a new positive or negative example came in. This was very important work in the field because it then led to, I think, a lot of work on symbolic learning in the 1970s. A number of researchers working in this area. My favorite of those was a system developed by Bruce Buchanan at Stanford called Metadendral. What this program did was it looked at training data, which was mass spectrum data from different molecules, and it learned from that data. By the way, in a mass spectrum, you put a molecule in the mass spectrum, it gets hit by energy, and it shatters, and then the mass spectrum tells you a histogram of how many chunks of different mass are observed after the shattering. So what his program learned were rules, symbolic rules, that characterize how those molecules shatter. And this rule, for example, says if you find this subgraph within the molecular graph, then expect it to fragment along these bonds. And there are some specifications of the details of the different atoms. Okay, so this was important because it actually worked. In fact, I asked Bruce Buchanan how well it worked. What was this program able to do in terms of, did it work?
Well, for one small class of steroid molecules, the ketoandrostrains, if you will, we had fewer than a dozen spectra, and we were able to tease out the rules that determined how a new keto-androsten would fragment in a mass spectrometer. And we were able to publish that set of rules in a refereed chemical journal, chemistry journal, sorry. And it was, to our knowledge, the first time that the result of a machine learning program, symbolic learning, had been published in a refereed journal.
So it really was a milestone for the field. This was the first time machine learning actually discovered something that was accepted as new knowledge in the field. Now, it turned out I was a Ph.D. student at Stanford at the time, as Leslie pointed out, and Bruce became my Ph.D. advisor. So my own thesis was based on the same kind of data, and I developed an algorithm called version spaces that was the first algorithm for which you could prove that it would converge, given correct training data, on the correct hypothesis. And you could prove that the learner would know when it had converged. It had a side, the way it did that was kept track of all of the hypotheses that fit the data. And this opened up also the possibility of what we now call active learning. That is, the learner could ask the teacher, can you label this example positive or negative? And then when the teacher did, the learner could ask a new question. And in this way, the learner could basically pay 20 questions and narrow down the set of hypotheses. Okay, so by the end of the 70s, there were a number of symbolic learning algorithms, and it seemed like it's worth having a meeting to get together people in this field. So we organized a meeting, and when I say we, I mean Jaime Carbonell, who was at the time an assistant professor at Carnegie Mellon, Richard Mikulski, who is a professor at University of Illinois, and myself, I was an assistant professor at Rutgers University. And we held a small workshop inviting all the people we were aware of who were working in this area. One of the people who attended was a student of Richard Mikulski named Tom Dietrich. Tom went on to make many contributions, but I got a hold of Tom and I asked him, what was the field like in 1980?
I'd say it was really chaotic. I attended that very first machine learning workshop that was organized. I think you were one of the co-organizers at CMU, and there were probably 30 people in the room, and probably 30 completely different talks. I remember, I was talking about, I had done a sort of algorithm comparison paper that I published at IJCAI 79, I think, so just before that workshop, in which I was by hand executing these very simple algorithms for this kind of subgraph learning problem and comparing how many subgraph isomorphism calculations they had to do. But it was like the first attempt to actually compare multiple machine learning algorithms that were more or less trying to do the same thing. There were a couple of them there. I think John Anderson was there talking about, cognitive models. You were there talking about the beginnings of EBL and the LEX system for calculus, symbolic integration. I remember the most interesting talk I thought was Ross Quinlan's talk on ID3, where he was trying to take these reverse enumerated chess endgames and learn decision trees that would completely, exactly, losslessly basically compress those giant tables into a small decision tree.
So I agree with Tom when he said that the most interesting talk at the workshop was Ross Quinlan's talk on decision tree learning. A decision tree is simply a structure where when it tells you how to classify the example, you put the example at the root of the tree, and then you sort it based on its properties down to one of the leaves, and then the leaf tells you how to classify the example. So I contacted Ross, and I asked him how he came up with the idea of decision tree learning.
I had done a PhD under a psychologist, Earl Hunt, and part of his work involved decision trees, which I learned about, of course, as a student, but then put in the back of my mind for 15 years or so. And then I was at Stanford on sabbatical at the same time as Donald Mickey was teaching a course on learning. And he had a challenge for the class on which, I sat in on the class. And the challenge was to work out a way of predicting a win in a very simple chess endgame, King Rook versus King Knight. So I remembered Earl Hunt's work on decision trees, and I thought, well, maybe that would be the way to go. So I developed a thing called ID3, which was just a simple decision tree program, no pruning, just straight decision tree. And then that seemed to solve the problem pretty well, up to about 95%. And then I got that up to 100 the next year. And then remember, the first real time I talked about this was at that conference you organized, the workshop in 1980 at Pittsburgh at Carnegie Mellon. You, Richard, and Jaime all set up that workshop, and then I gave a talk on decision tree learning.
So this was also a very important event in the field because by 2010, decision tree learning and decision forests were kind of one of the dominant methods commercially for machine learning. And Ross went on to form a decision tree learning company and did a lot of work in this area. So by the early 80s, there was kind of this bubbling cauldron of ideas and people trying different experiments in machine learning. But really, there was no decent theory. Now, what would you want a theory of machine learning to tell you? Well, among other things, it would be nice if it could tell you how many training examples do I have to show my algorithm in order for it to learn reliably. Well, that problem was addressed in 1984 by Les Valiant. And Les introduced what came to be called, thanks to Dana Anglewin, came to be called PAC learning, or probably approximately correct learning. And his theory told us how many training examples you need, and that it depends on exactly three things. One, it depends on the complexity of your hypothesis space. So for example, if you're learning decision trees of depth 2, of maximum depth 2, that's not very complex compared to somebody's algorithm that learns decision trees of depth 22. So the complexity of the hypotheses is one thing you depend on. Another is the error rate you're willing to put up with. Are you willing to put up with 1% error, 2% error? The third thing is the probability that even if we do give you M training examples drawn at random from the training pool, the probability that you're still going to fail. And it turned out you couldn't guarantee no failure if you have probabilistic drawn examples, because you might get a bad, unlucky draw. But it took this kind of reframing of the problem in order to be able to prove a quantitative relationship between a bound, to prove this bound on the number of examples you need to achieve reliable learning in that probably approximately correct sense. So this was a major event in the field. So I asked Les how he thought this related to the field.
It's a kind of a model of computation, but it makes sense because it's got some applications. So just first, the particular result which persuaded people that there was something there is this result that if you take a conjunctive normal form formula, which from NP completeness at the time we already knew, there's some hardness in it, because if someone gave you the formula was computationally difficult to find out whether it's null, whether it's equivalent to formula which is always zero, which is never satisfiable. On the other hand, this was kind of this contracting normal form formula with three variables in each clause. So this was pack learnable. And so this was a bit striking that something which is very hard is learnable. But then this highlighted the difference between computing and learning. Because so with the learning model, the idea was that there was a distribution of inputs, and you learned from this distribution, but you only had to be good on this distribution when you had to predict. So if, for example, in this formula there were some very rare ones which are so very rare, then the learner wouldn't have to know about that. So in this sense, this was easier than the NP completeness.
So another way of saying what he's saying in our machine learning terms is he's saying that he thought the interesting result that captured people's attention was this. If your hypotheses are a particular logical formula style called conjunctive normal form, then it was already known that answering the question, is there a positive example that will match this formula, was NP complete. What that means is the cost of computing that answer, is there a positive example, is exponential in the size of the logical formula. But he was able to show that if instead you're trying to learn the formula from positive and negative examples that people give you, then it only costs you polynomial work, less than exponential in the size of the formula. So I agree that's a theoretically really interesting result, but if you ask me the impact of this on the field, I would give a totally different answer. The impact on the field was so important because he came up with a reframing of the machine learning problem, where now all of a sudden examples were being drawn at random from some probability distribution that was unknown to the learner but just fixed, couldn't change. And the test examples would be drawn from the same distribution. And that was an idea kind of borrowed from statistics. But to put it all together, he came up with a new framing of the problem that allowed there to be a theoretical result like this. And then people took off with it and ran with it for decades. And to this day, there's a conference called the Conference on Computational Learning Theory that really was ignited by this work. So that was 1984.
It's
Oops. There were also in the 80s people looking into how do humans be intelligent and learn? And one of the groups looking at that was led by Alan Newell and involved his students, John Laird and Paul Rosenblum. They developed agent architecture in which their goal was to build an agent that could exhibit the full range of cognitive abilities of a person. Instead of building a machine learning system to play checkers or to classify flowers, they wanted an agent that could play games, perceive the world, solve puzzles, plan actions, and everything. And so this work was interesting in the sense that I think there are still very good agent architecture ideas in their source system. And I'm not going to have time to play a video, but in the podcast that contains all these videos and more, there's a video interview with John Laird who talks in more detail about this. So elsewhere in the 80s, a really important event was the return of neural networks. Remember, they had been kind of banished from the field by this 1969 book by Minsky and Papert, which showed that perceptrons couldn't really learn anything if they could only learn linear functions if they were just one-level perceptrons. And that was all we knew how to train. Well, in the mid-'80s, people discovered that you could train multiple layer neural networks, which would produce highly nonlinear decision surfaces. And this was important. 3 of the ringleaders on this were Dave Romelhart, Jay McClellan, and Jeff Hinton. So I asked Jeff about this period. Now we're up to the mid-'80s when really neural nets are reborn. Is that the right word? How would you
Yes, with
characterize?
backpropagation. I mean, we didn't invent it. It was invented by several different groups. But we showed that it really worked to learn representations. And as you know, sort of one of the big problems in AI is how do you learn new representations? How do you avoid having to put them all in by hand? And my particular example, which was the family trees example, where you take all the information in some family trees, you convert it into triples of symbols, like John has father Mary, and then you train a neural net to predict the last term in a triple given the first 2 terms. So it's just like the big language models. You're predicting the next word given the context. It's just much simpler. I had 112 total examples, of which 104 were training examples and 8 were test examples, which is a bit less than the trillion examples they have nowadays. But it was the same idea. You convert a symbol into a feature vector. You then have the feature vectors of the context interact via a hidden layer. They then predict the features of the next symbol. And from those features, you guess what the next symbol should be. And you try and maximize the probability of predicting the next symbol. And you then backpropagate through the feature interactions and through the process that converts the symbol into features. And that way you learn feature vectors to represent the symbols and how these vectors should interact to predict the features of the next symbol. And that's what these big language models do.
So there's Jeff's summary. So this all happened around 1986, 87 was when a book came out, the Parallel Distributed Processing book, which was a compendium of papers edited by Jay McClellan and Dave Romelhart, and Jeff had been involved. Personal note, 1986 was also the year that I went on leave from Rutgers to spend a year as a visiting professor at CMU. And while I was there, Alan Newell, who had been working on the SOAR program I just mentioned, asked me, hey, would you like to team teach a course? We'll call it the course on intelligent agents. And I said, sure, Alan Newell, chance to teach with him. And he said, by the way, there'll be a 3rd person joining us, an assistant professor named Jeff Hinton. So Jeff and Alan and I taught a course in spring of 1986 on basically AI machine learning. It was a great event and one of the reasons I ended up permanently at CMU. So when I moved to CMU, then the next year though, Jeff moved on. He went to the University of Toronto and started setting up a group there and hired a postdoc named Jan LeCun, who was just had finished a PhD and was now looking for a postdoc position. So I asked Jan what it was like to join Jeff's group.
And then mid-1987, I moved to Toronto to do a postdoc with Jeff. And I completed the simulator. Jeff thought I was not doing anything because I was just basically hacking all the time. And this system was kind of interesting because we had to build a front-end language to interact with it, and that language was a Lisp interpreter that Leo and I wrote. And so we're using Lisp, even though as a front-end to kind of a neural net simulator. And I implemented the weight sharing abilities and all that stuff and started experimenting with what became convolutional nets, when I was a postdoc in Toronto, early 1988. Roughly, and started to get like really good results on, very simple shape recognition, like, handwritten characters that I had drawn with my mouse or something like that, right?
So as Jan said, as a postdoc, he was starting to get very interesting results on character recognition using something he had been working on called convolutional nets. And during that period, the late 80s, neural nets were beginning to encroach just as symbolic learning had displaced perceptrons as the new paradigm. Neural nets were encroaching on symbolic learning. And there were more and more experiments to try to understand what could neural nets really do. My favorite demonstration of the decade was what turned out to be Dean Pomerleau's PhD thesis. He trained the first neural network that could do self-driving cars. His neural network took as input an image that you capture looking with a camera out the windshield of a vehicle, and as an output, it would tell you which direction to steer. So I asked Dean about that. In the end, how much training data did you have?
So the interesting thing was, to begin with, it was all batch training. So I'd have a person drive the vehicle along Shenley Park, Flagstaff Hill path, and then I would go off and crunch it overnight. But in the end, what we were able to do is real-time learning. So one drive up the hill with a human behind the wheel steering, and the neural network learning to pair images with camera images with the steering command that the human was giving, was able to train it in about 5 minutes to take over and steer on its own from there on that road and on similar roads. So it was one of the first real-time, real-world vision applications of artificial neural networks. Going beyond just Flagstaff Hill, you know, the little paths on there, and we went out on real roads, first through the golf course, Shenley Golf Course on the road there, and then we went on, you know, the local highways. In fact, the longest, as part of my PhD, the longest trip we did was, I think, about 100 miles at the time, from basically up I-79 from Pittsburgh all the way up to Erie, and it drove basically the whole way. So it was getting up to 55 miles per hour after we got a faster vehicle.
So yet another 1980s thing was the advent of reinforcement learning. And the idea of reinforcement learning is, for example, in Dean's case, he trained his system using what we call supervised learning. That is, you have a neural network that, given an image, should predict a steering direction. The way he trained it was to get human supervisors to drive the car so that he could capture training examples that gave, here's the input image, and here's the correct steering command. The idea of reinforcement learning is, what if you don't have a trainer? So for example, if you're learning to play chess or checkers, you might have somebody who tells you at each board position which move to take, but if you don't have a trainer, then you have to just make moves and wait until the end of the game to find out if you win or lose. So reinforcement learning was, again, a reframing of the machine learning problem to a slightly different problem that changed the nature of what kind of algorithms you needed to use. Rich Sutton and Andy Bartow were key innovators in this. So I asked Rich how reinforcement learning related to the rest of the field.
The field of machine learning has always been dominated by the more straightforward supervised approach. And there's, as I mentioned, at the very beginning, the rewards and penalties were very much a part of it, but then the focus, as things became more clear and more better defined, and it became a more clearer learning problem, then it became pattern recognition and supervised learning. And this fellow, the strange fellow Harry Klopp, recognized this more than other people, and wrote some reports and ultimately a book saying that something had been lost. And Andy Bartow and I picked up on his work and eventually realized that he was right, that something had been left out. And in some sense, it was obvious that something had been left out from the point of view of psychology, where I'd been studying how animals learn, and animals learn really in both ways, in both a supervised way and a reinforcement way. And so, so we picked up on that and made that into a well-defined area in the, when was that? That would have been in the 80s. And then finally we wrote a book on it in 98. So then it became a clear subfield of machine learning. Yeah, but the key thing is, why is the way I say it to myself is that why is reinforcement learning why is it powerful, potentially powerful? And it's powerful because it's really learning from experience, learning from the normal data that an animal or a person would get. And it doesn't require a prepared special data like you of course do in supervised learning.
So the 1980s really was a time of very broad exploration, very creative decade if you think about all of these innovations that happened. And there was more. People were looking at things like maybe we can simulate evolution as a strategy for learning. In fact, there was a conference that went on for many years called Genetic Algorithms Conference, later Genetic Programming, and many other approaches people were trying out. But then when we moved into the 90s, again, there was a shift, really. In the 1990s, suddenly there was a movement toward importing ideas from probability and statistics. And much of that took the form of what people call probabilistic graphical models or Bayes nets. The idea is you have a bunch of variables and probabilistic relations among them. You might be interested, for example, in whether somebody has cancer, and you might have observations like whether they're a smoker, what their X-ray result is, and so forth. And then the edges in the network represent probabilistic dependencies among these variables. And taken together, that whole graph represents the joint probability distribution across the entire set of random variables. So this was a representation really developed by Judea Pearl in the late 80s, who went on to get the Turing Award for that work. But Judea did not really have a good algorithm for learning these. That remained an open question. During the 90s, machine learning researchers started looking at that question. And one of the key innovators there was a Stanford professor named Daphne Kohler. And so I asked Daphne why we needed probabilistic graphical models.
Probabilistic graphical models, for me, emerged by realizing that the problems that we needed to solve to address most real-world applications went beyond you have a vector representation of an input and a single, oftentimes binary or at best continuous output. There was so much more opportunity to think about richly structured environments, richly structured problems. So even if you think about problems like understanding what is in an image, that's not a single label problem of there is a dog, because images are complex and there is interrelationships between the different objects. You wanted to get beyond the yes, no, is there a dog in this image, to something that is much more rich. There's a dog and a frisbee and a beach and 3 kids building a sandcastle. You have a rich input and a rich output. Thinking about these richly structured domains gave rise to, we have to think about multiple variables, we have to think about the interactions between those variables and leverage that structure both in our input and our output space in order to get to much better conclusions and deal with problems that really matter.
So this was a key theme of the 1990s in machine learning, was how do we learn these kind of probabilistic models from data? But that was really, the Bayes nets were really just one piece of a larger movement of importing statistical ideas into machine learning. Another researcher who is very instrumental in that was a Berkeley professor named Mike Jordan. So I asked him about the relationship between statistics.
So anyway, by the time I wanted to move to Berkeley, I was realizing that I was missing the whole statistics community, that it was just separate from machine learning. As maybe you kind of remember, there was occasionally a little leakage, but it was way too separate. And nowadays we're often seeing, people will run a machine learning method, but then it's not calibrated. It's not, it has bias and all that. And that's the thing statisticians have talked about for a long, long time. And so nowadays, I think it's a given that, yeah, they're kind of two parts, two sides of the same coin. Machine learning is maybe a little more engineering oriented. Let's build a system and make it do great things in the world. And statistics is a little bit more, well, let's be cautious. We're going to do like clinical trials. Let's make sure that the answer is really trustable. But those are two sides of the same coin. And I think that's probably pretty much clear now. But for a long time, there was a resistance. Everyone said, this is a brand new field. This is different. And I kept, again, annoying colleagues by saying, no, I don't believe it is. So anyway, long story short.
It is remarkable that, to me, that the field of machine learning went through most of the 1980s kind of without even noticing that statistics exist.
I mean, people like Leo Breiman were around to help make the passage. So ensemble methods, they were kind of invented by Leo, and so it's stat literature, but they were independently invented in the machine learning literature. And is that machine learning or statistics? Well, clearly it's both, and it needs both perspectives. And yes, in the 1990s, the EM algorithm, the graphical models, they had. So yeah, in the 90s, it was a real flourishing of that.
So again, in the 1990s, yet another paradigm comes in to kind of wash over the earlier ones. And at this point, one really interesting thing is neural networks fell completely out of favor. So they were riding high in the late 80s, but in the 90s, when people got interested in statistics and probability, many of the statisticians, I always smiled when I'd hear their talks, because they would always talk about the principled statistical methods that they were using. And they just left you to fill in the blank of what was the adjective that went before neural network. Clearly it wasn't principled. And so for various reasons, work in neural networks pretty much died off. There was actually a conference called NeurIPS, Neural Information Processing, that was launched in the late 80s to cover neural networks research. There was 1 year where there were basically 0 papers published on neural networks in that conference. There were so few people working in that area. But so during the 90s, this was very much the theme, and into the early 2010s. And there were other things going on too, to be fair. The invention of methods like kernel methods, support vector machines, which are a mathematical scheme for learning highly nonlinear classifiers that happen to be linear in some other space if you project the data into a very large space. But through the mathematical kernel trick, you didn't actually have to work in that large dimensional linear space. You could use these tricks to make very efficient computations. There were various ideas going around through the early 2000s, but for me, the theme of the decade of 2000s was really a kind of creeping feeling that maybe we have good enough learning algorithms. And maybe the bottleneck is no longer we need a better algorithm. Maybe the bottleneck is we need more data and more computation. And this was kind of crystallized in this wonderful paper from 2009 by 3 Google researchers called The Unreasonable Effectiveness of Data, where they documented several case studies where even though people would try to come up with better algorithms, the key was just getting more data. And so there was this kind of lingering feeling in the field that something was happening here. Oh, and by the way, during this period was a great period for commercialization of machine learning. There was a lot of use of machine learning for things like marketing and many other kinds of problems. But then things really blew open in 2012. That's when, well, let me give you the background on this. A researcher named Fei Li had put together and published a data set of images labeled by the main thing in the image. And this was being used by the computer vision community to test out different computer vision algorithms. Who could do the best job recognizing the objects in the image? And in 2012, at the annual computer vision conference, Jeff Hinton, remember him? Neural Net's Jeff Hinton and his students entered the contest and blew away the competition with a neural network solution. So this was quite significant because it marked the return of neural nets. So I asked Jeff about that. Here's Jeff's answer.
And Jan realized when Fei came up with the ImageNet dataset, Jan realized they could win that competition. And he tried to get graduate students and postdocs in his lab to do it, and they all declined. And Ilya Sutskever realized that backprop would just kill ImageNet. And he wanted Alex to work on it. And Alex didn't really want to work on it. Alex had already been working on small images and recognizing small images in CFAR 10. And Ilya pre-processed everything for Alex to make it easy. And I bought Alex 2 NVIDIA GPUs to have in his bedroom at home. And Alex then got on with it, and he was an absolutely wizard programmer. He wrote amazing code on multiple GPUs to do convolution really efficiently. Much better code than anybody else had ever written, I believe. And so it's a combination of Ilya realizing we really had to do this. And Ilya was involved in the design of the net and so on, but Alex's programming skills. And then I added a few ideas like use rectified linear units instead of sigmoid units, and use little patches of the images. I mean big patches of the images, so you can translate things around a bit to get some translation invariance, as well as using convolution, and use dropout. So that was one of the first applications of dropout, and that helped by about 1%. But it helped. And then we beat the best vision systems. The best vision systems were sort of plateauing at 25% errors. That's errors for getting the right answer in your top 5 bets. And we got like 15%, 15 or 16, depending on how you count it. So we got almost half the error rate. And what happened then was what ought to happen in science, but seldom does. So our most vigorous opponents, like Jitendra Malik and Andrew Zisserman, looked at these results and said, okay, you were right. That never happens in science. And slightly irritatingly, Andrew Zisserman then switched to doing this. He had some very good postdocs or students working with him, Simonian. And after about a year, they were making better networks than us. But that was really as far as the general public was concerned, that was the start of this big swing towards deep learning in 2012.
And it really was. It was a wake-up call, not just to the computer vision community, that neural nets were a significant approach they should be looking at. And by the way, within a couple of years, the majority of the competitors in the computer vision community were neural network based. But more generally, it was a wake-up call to the whole machine learning community that maybe we had been a little too hard on neural nets earlier. And this new generation of neural net algorithms called deep nets, which could train networks not just with 2 layers, but with dozens of layers, really was pretty effective. So just like in the late 80s, this set off a flurry of activity of people looking at, well, what can we use these neural nets for? And they would, it turned out they were very, very good at perceptual data. So people were using them for Well, for
And
example,
Jan realized
for speech recognition, for example, by 2016, Microsoft researchers had used deep networks to finally achieve human-level word recognition accuracy on a data set called Switchboard that had been a long-running data set used in the speech recognition community. But people were also looking at applying this to LiDAR, to radar, to all kinds of sensory perceptual data. Now, some people then decided, can we apply this to text? What about text? And it turned out, yeah, you kind of could. But you had to deal with the fact that text was really a sequence of tokens. It's nothing like an image. Convolutional nets were not the way to go. And people started inventing different architectures for neural network architectures for handling word sequences, and with names like long short-term memory and various things. And commercially, groups like Google got very interested in this, and in particular applying it to machine translation, translate French to German to English. And it was kind of pretty good at that. But then, as that work was going on, in 2017, the most consequential paper of the decade came out. It was called All You Need is Attention. Attention is all you need, sorry. And the point was, what attention? Attention is just a sub-circuit used in neural networks. I think of it as a trainable if-then statement, but talk to me later about that. But it's a particular way of organizing neural networks. And this paper came out that showed they could achieve an advance in machine translation by using a simpler architecture called the transformer that was based on attention. And this was very important because it was also very parallelizable. You could use multiple GPUs and parallelize the computation. Now, around this time, Jan LeCun, remember the postdoc who worked with Jeff in 1987, and who, by the way, went on to co-win the Turing Award with Jeff and Yoshua Bengio. Jan LeCun, by then, was both a professor at NYU and chief AI scientist at Facebook Meta. So he was in a very interesting position because he could see commercially what was going on, and he understood the academics all the way down. So I asked him to describe this period. And he starts by saying that he thought one of the most important early developments was the switch from thinking that we had to have humans label all the data to having what we call self-supervised data. That is, doing things like take a string of words and just say, I'm leaving out this middle word. The problem is to predict the middle word. Well, if you could do that by program, and it knows what the middle word is. You don't need a human to label the data. So his point was that the first important development was the widespread recognition that we could get much larger data sets by having self-supervised learning. Then he went on from there.
So the idea that self-supervised learning could really kind of bring something to the table there, I think, was kind of a big sort of mind change of mindset, and then there was transformers, of course, right? So before that, there was some demonstration that you could basically match the performance of classical systems for tasks like translation, language translation, using large neural nets like LSTM. So this was the work by Ilya Sutskever when he was at Google. We had this big, sequence-to-sequence model with LSTMs and some, gigantic model. where you can train it to do translation, and it kind of works at the same level, if not better in some cases, than the then classical translation methods. And then a few months later, Yashua Bengio, Dmitry Badanao, and Kyung-Young Cho, who is now a colleague at NYU, showed that you could change the architecture and use this attention mechanism that they proposed to basically get really good performance on translation with much smaller models than what Ilya had been proposing. And the entire industry jumped on this. Chris Manning's group at Stanford kind of used that architecture and basically beat won the WMT competition for a particular type of translation, and the entire industry jumped on it. So within a few months after that, all the big players in translation were using attention type architectures for translation. And that's when the transformer paper came out. Attention is all you need. So basically, if you build a neural net just with those kind of attention circuit, you don't need much else, and it ends up working super well. And that's what started the transformer revolution. And then after that came BERT, that also came out of Google, which was this idea of using self-supervised learning, right? Take a sequence of words, corrupt it, remove some of the words, and then train this big neural net to reconstruct the words that are missing, predict the words that are missing. And again, people were amazed by how good the representations learned by the system were for all kinds of NLP tasks, and that really kind of captured the imagination of a lot of people. And then after that, the next revolution was, actually, the best thing to do is you remove the encoder, you just use a decoder, and you just train a system. You feed it a sequence, and you just train it to reproduce the input sequence on its output. And because the architecture of the decoder is strictly causal, because a particular output is not connected to the corresponding input, it's only connected to the ones to the left of it, implicitly you're training the system to predict the next word that comes after a sequence of words. That's the GPT architecture that was promoted by OpenAI. And that turned out to be more scalable than BERT. And so in a sense that you can train gigantic networks on enormous amounts of data, and you get some sort of emergent property, and that's what gave us LLMs.
So that pretty much brings us up to today. So you can see there was this flurry of activity, and a bunch of it was now suddenly in companies rather than universities, and that's how we got to GPTN since then. So we could end here, but I want to take one more minute just to step back and say, if we think of this as a kind of case study of scientific progress, then what are the themes we see and what are the lessons? So I think the themes we see, the first one I see is that progress really happened in waves of new paradigms coming in, washing over and pretty much replacing earlier paradigms. We saw perceptrons replaced by symbolic learning, by neural nets, by probabilistic methods, by neural nets again. That's the way this field moved. Second one is that really many of these ideas came from other fields. Even perceptrons came from somebody who is fundamentally looking at neuroscience questions. And Bayesian networks came really from motivation from probability and statistics. So there were many ideas imported. A third theme, many of the advances were really making up a new framing of the problem. That's how Les Valiant was able to develop a theory of machine learning. He changed the definition a little bit. That's why reinforcement learning became popular, because those guys said, what if we don't have a teacher? So reshaping, redefining the problem. And then, like many fields, really progress was the result of both technical advances and social dynamics. And if you ask me, the good news is that in the long run, I think the cold hard facts of what works really do determine where the field ends up. But in the shorter term, much of the energy of the field and the problems that PhD students decide to work on are strongly influenced by social factors like what their advisors are saying and what famous people in the field are saying. So given all this, what are the lessons for us as researchers? I think the first one is question authority. Because if you really think about these advances, they mostly came from people who went in a direction not quite the same as the conventional wisdom of the time. Second one is don't drag your feet. I can tell you, decade after decade, I have seen as a new paradigm comes in, especially the senior researchers in the field saying, oh, that won't really work. You have to stick with my paradigm. And it's really, especially the senior researchers who drag the feet the longest. Eventually, if the paradigm really holds water, they will, of course, shift. But in many cases, they shift much later than they could have. The third one is learn to communicate and follow through. You heard Jeff Hinton say, we didn't invent propagation. We just showed that it was useful. And they actually thought they had invented backpropagation, but later it came out that somebody had invented it years before, and nobody knew. And how could that be, you could ask yourself? Something as important as learning how to train multi-layer neural networks. It was a researcher in Finland who came up with this idea, but nobody knew about it. Why? I'm not sure the reason, but maybe it was some combination of he was from Finland and not part of the usual crew that we listen to. Maybe he didn't follow up by demonstrating to the field that not only here's another algorithm, but it's a useful one. So I think the moral of this story is if you have a good idea, you might know it. You have to make sure everybody else knows it. And then the final lesson is actually the philosophers were right. There is no justification or proof that you can generalize from specific examples to general laws and be correct, despite the fact that we have ridiculously successful LLMs these days. And so I think it's worth going back and thinking this through and trying to understand why is it then, and in what conditions would it be then that, say, LLMs and the transformer architectures that we're training are actually getting good generalizations, despite the fact that that's not guaranteed. All right, I'll stop there. Thank you. If you find this interesting, I'll just put this up.
We can take some questions?
Yes?
Thank you, Professor. I very appreciate your talk. That's great history about this technology development. And my question is about, since nowadays LLM already extends to the society. So, what kind of new structure could be if you can image about this new structure with the social technology structure nowadays?
Social technology structure. I'm not sure what exactly you're getting at. Give me an example of a social technology structure so I know.
For example, like we see what you talk about is from calculation, neuroscience, and also the lots of the this kind of the ideas from like even like expert gates, like also like this could from the social structure, social behaviors. So I just wondering. So nowadays already, I mean, it's not just a model in in technique layers, but still extend to the calculation layer and the institution layer. So just wondering how we can image the
I see. Well, that's a pretty challenging question, but if I dream big, then my answer would be the new structure is going to replace the current paradigm of Lone Ranger research. That's basically the paradigm we're all here for, right? We have maybe a team of a handful of colleagues who we work with. We write a paper. Usually they have 10 or fewer co-authors. We write the paper, we publish it, and we move on. But there's no reason that I can think of why that should be the optimal strategy. And now that we have communication networks that we never had 30 years ago, and ways of sharing data that we never had 30 years ago, and ways of, and things like GitHub. What if we had a GitHub for research hypotheses, for models, for experiments that we thought should happen, and agents that could run off of that kind of framework. So, I mean, I don't know exactly how to make that happen, but it does seem to me that if you look at the idea of Lone Ranger research, which is really what I've been talking about up until the last 5 years, then there's another alternative that we could explore. I think it'd be worth it.
I want to intervene. Good. We'll take Nancy and Josh, and then there's going to be a reception outside.
Sounds good. Nancy.
Just a beautiful story. Thank you so much for that. One thing that was really salient to me, and I'm sure others, is there were almost no women. There was Daphne Kohler and Pepe Lee.
Yep.
And I wonder what your thoughts are on why so few, because of course that's half the brain power of the planet not being missed out on this enterprise, and what can be done about it.
Yep. So you're not the first person to ask me that question. The first person to ask me the question was when there were 0 women in my set. And Daphne totally deserves to be there, and it was just, there were also men who showed up here who weren't in my set yet either. It was incomplete. Daphne definitely belongs there as one of the key innovators. My answer to your question is, for whatever reason, the historical record is these were the people.
Yeah, I guess my question is, why do you think that was true?
Oh, I think it was true because, let's say, during the 1980s, there were very few women compared to the number of men in computer science research. That has changed dramatically, obviously, here, to the point where in many universities it's sort of 50-50 these days. So I hope when we give this talk 50 years from now, the ratio will be different. But this is just the historical fact, and I agree with you that it would be good to change it. And as you know, there are many efforts to make that change. But I can't apologize for just reporting the news. Josh?
I have further thoughts on that, but I'll save those for later. I think actually the story is more complex than that. But we can discuss that later. Or maybe I should say, the men have been a lot better at promoting themselves and putting their image out there and their voices. And there's a whole dynamic around that and how that's promoted.
Yeah.
And I think you have to, we all have to acknowledge that as well. There were a number of prominent women that you mentioned, that you just mentioned, but didn't put their pictures or their video up there, but you mentioned them. So there's also the issue of like whose image goes up there and whose voice do you hear versus who is just quoted.
Yep.
So I think we should all acknowledge that. But the question I was actually going to ask you about is, first of all, thank you for a very beautiful talk, for all the parts that you did include. That's great. But I was a little disappointed that there wasn't more forward-looking stuff at the end. Like you referred to some things like in the source section, the talk about architecture, like, oh, there's some good ideas still here. Like, so I want to just give you the opportunity to say, like, do you think the history of machine learning is over? Did it just end with LLMs, or are there?
No. No. Thank you.
Some guidance for what to do in the future that isn't just where we are right now.
Thank you for that question. The reason there was not more future is I ran out of, you can see the talk was long enough as it was. But there's a very interesting future for machine learning. It's not anything like the past. In the past, if you had asked anybody in the field in the year 2020, what's the mechanism by which computers learn? Their answer would have been 90% of people would have said parameter tuning. And they would have been right. Neural networks, you're tuning parameters. Decision trees, it's a structural parameter, but yeah, it's parameter tuning in some predefined kind of model. Okay, now we have LLMs, and we have an opportunity, just as SOAR did, to start looking at what if we build agents that use LLMs as subroutines to do whatever reasoning and whatever perception we want them to do. But they're agents, and they have sensors and effectors into the world. Many people are interested in this problem. Think for a minute how it changes the machine learning question. Now if I ask you, what are the mechanisms for learning for that agent? Yes, they can still tune the parameters. For example, post-train the LLM that's inside them that they're using. But they can also change their behavior in other ways. They could write software, build up a software library, and use that software library to do things that they couldn't do before. It's a different way of changing behavior. They could also write themselves a bunch of text files, an encyclopedia of the things they have learned from their experience in the world. And just those three things alone, parameter tuning, code development, and encyclopedia writing, are three learning mechanisms that define, I think, a huge part of the future for machine learning. So we're no longer trapped in this bubble where we have to think of learning as parameter tuning. The sky's the limit. We can, this code can modify its own code, write new code, can write down facts of what it has learned, can still do parameter tuning. We don't have any theory about that. What does it mean? What do you want a theory of those kind of systems to even answer? We don't have any theory. We don't have any. We barely have any algorithms. We barely have any papers that talk about learning in that way. So to me, it's like a new slate, a clean slate. But don't be trapped into thinking you have to work in the old bubble, because you don't. And it's not going to be a very productive bubble for very long. Yeah? Oh, there, okay, last question.
Do you think the field of machine learning would be in a trajectory that could get closer to answering the question about the human mind, how the human mind learns and works?
So if you ask me to rank order different fields that are liberated by these developments, cognitive neuroscience is very near the top of my list. I think there's a huge opportunity for using what we now see going on in AI systems as a kind of structure to learn more about the brain. I'll give you an example. Several people have shown, for example, that if you show a neural network an image and show the same image to a person in an fMRI scanner, then with a simple linear mapping, you can predict much of the neural activity in the brain in visual cortex from the artificial neural network activity of the artificial neural network that's processing the same image. So there's a correspondence between the hidden activations in the artificial neural network given the same image as in the brain. People have shown the same thing for various aspects of language. If you show the same sentence, word by word, to BERT or some of these LLMs, you can predict to a surprising degree the neural activity in the brain reading the same sentence. So we now have an opportunity that we never had before to use this these artificial AI systems as a kind of scaffolding to create hypotheses, to make predictions, to try to understand at a more granular level of detail the processes we see in the brain. And I think I'm out of time, so I won't take any more questions.